I'm not saying anything anymore. All right, so welcome back. Uh, Final lecture, which is interesting. Things go by so fast. So today, as I said before, I want to talk about kind of a bunch of other things that we didn't really discuss in the class. A couple of things. Don't forget your exam on Wednesday. Don't forget your final project, and also don't forget the feedback form. That's also important for us. Does anybody have any questions before we get started? All right, so today I want to mainly talk about kind of like the future, kind of the current and future, and kind of if you talk about computer architecture these days, you have to talk about NVIDIA as the kind of like now it's the most successful computer architecture related company. I kind of borrowed some of their recent keynote talk. So essentially what is happening now is that, when we talk about computer architecture these days, you have to talk about machine learning and the need for what we call data-centric computation. So really the trend in computer architecture has been that for longest time we decided to do more of what we call general purpose computing, right? The store program order that I talked about many times in this class. And why is it not moving? Oh, okay, maybe it's because of this. We talked about this store program order system that you have this sequence of instruction, and then essentially you design a system that can fetch this instruction and run this instructions, right? But then when it comes to some other applications necessary, this kind of like instruction-based approach may not be the best thing, mainly because there are some other quote unquote what we call kernels that this sequence of like operations, mathematical operations, that if you can actually kind of design a hardware for these kernels, then you can actually kind of like upload this kernels into the hardware and run them, and then run many of these kernels on your system. And there are many different possible kernels you can think about, but the ones that are like really effective is matrix multiplication. So essentially, people have found that there are tons of these kind of uh, algorithms that at its core it's really matrix multiplication. And if I can do this matrix multiplication really fast, then I can do lots of things very efficiently, including any sort of like neural networks or other variants of machine learning. So what happens is that the shift from that, oh, let's say we have a bunch of these instructions, we have if then else's and so on and so forth, has changed to how can I build hardware such that I can multiply two large matrix as fast as possible. Okay, if I can do that, then the rest is kind of like data orchestration. I need to bring the data, and then I need to store the data and all those things. So I essentially built kind of a harness around this kind of core capability, and then we will have what we call the domain-specific accelerator or domain-specific machine that is specific from that domain, and this particular thing is just matrix multiplication. So really at its core, these kind of quote unquote new architectures, these special architectures, what they do is that they can do a few mathematical operations very fast. And as I said, most of them, what they really do is just a very fancy matrix multiply. Okay. So essentially, this is kind of like where we are heading to, and most of these systems can do this kind of type of different matrix multiplication very quickly. And then this is kind of like how GPU has been born and designed, and now like one step further, people thought that okay, GPU, even you may not need to just have a GPU, you can have just basically the matrix multiplication, because GPU still have some knowledge of and notion of instructions and sequence of instruction and all those things, but you can actually say that no, what I really care about is just matrix multiplication. Let's actually build hardware for them. And I'm sure that you guys have taken courses around like AI on chip or generally like machine learning accelerators and things like that. If you haven't, I definitely recommend you, if you're interested in this kind of topic, consider taking that at some point. But as I said, long story short, the idea is, can I build hardware that can do these things very fast? 5 years, 10 years from now, there might be another like kernel, another specific mathematical operation that requires this kind of design. But for now, the king is matrix multiplication, really, right? And now what is happening is that, you know, what we are seeing now is that we just need more and bigger and faster multiplications, right? We need large, and the reason for this is that these models are getting bigger and bigger, right? They can be deeper and deeper with more parameters. So if I can do many more multiplication at the same time, essentially I can do the inference faster, right? And this is what is really happening, right? So like the y-axis here is showing the model size, right? And the x-axis is the year, and then these points are different, very well-known models, right? The Llama 2 and Llama 1 and GPT-3 and GPT-2 and so on and so forth. And really what is happening is that the difference between these are kind of the model structure itself, which at its core, thankfully, is still matrix multiplication. Some of them are fully connected, some of them are transformer based, some of them are convolutional neural networks, so on and so forth, which if you're familiar with machine learning, you'll know the difference between them. But at the end of the day, as a hardware designer, what you really need to be able to do is being able to run that kernel as fast as possible, right? And I think personally that at some point we might see some other operations that are going to be baked into the system, and we're going to see the hardware going to be evolved around it. But what we're going to see in the next 5 to 10 years is essentially this. That's why, as a hardware architect, you probably need to understand the underlying design of these, but also you need to understand how to architect this particular kind of systems. And then here is kind of like, the GPUs and the memory. Important thing about when it comes to this database, like data-centric computation, is that no longer doesn't matter like how much fast your hardware is. It really depends on how fast you can bring data from the memory to the CPU. If you remember, a long time ago, we said that this is the CPU, this is the memory. What is really happening is that we make this CPU really, really fast, but unfortunately, the memory cannot keep up with that speed, because fundamentally, the technology for the memory is very different than the CPU, right? So we make this really, really fast, but this one is kind of like, lagging a little bit. And now that we need to bring millions and millions of data to the CPU or to our GPU or to our accelerator, now that this memory bottleneck is even worse, right? So what we really need is coming up with this newer technology of how we can actually pump out data from the memory as fast as possible. And one of the key technologies is what we call high bandwidth memory, HBMs, that what it does is that it's using this newer technology in order to make, the data movement between the memory and the processor faster. So these are kind of like the technology at its core of these designs. For example, NVIDIA, what they're really trying to do is like developing these faster memory technologies, HBM2, 2E, 3E, and so on and so forth. So what really makes these GPUs really, really fast these days is that they figure out ways to kind of like, read this memory and move this data from the memory very, very fast. Okay. Any questions so far? All right. So another thing that is happening, and kind of like to add into this kind of like technology, is the way that we put our CPU next to our GPU next to our memory. This is again the picture that I got from Blackwell, which was introduced very, very recently. And Blackwell is quite interesting. This is actually what they showed, is that they have these two GPUs, two Blackwell GPUs right next to each other. And then this is their CPU that they have. They call it gray CPU. And the big thing about like how they managed to put this very large GPU next to each other is a technology that they use in order to put very, very large piece of silicon next to each other, okay? So in the past, what we had was essentially we started like a long time ago with like building ICs, right? Integrated circuits. We managed to kind of put more and more transistors into a silicon chip. And we got really, really excited and then managed to put more. As we put more, then we had faster computers. Most of you know about Moore's law. So essentially what Moore's law is saying is that we can double the number of transistors every almost 2 years. So it's kind of like something like this, that this is the year and this is the number of transistors. And because that we kind of like had good technology, we kind of shrink the size of the transistors, we put more and more transistors into the ICs, okay? And then what we saw is that, okay, now we can also increase the size of this IC. We can just, not only we can shrink the size of the transistor, but we can also increase the size of the IC. So ICs get bigger and bigger and bigger, right? And we managed to put trillions and trillions and trillions of transistors, as you can, if you follow, for example, the Intel generation, M1 versus M2 versus M3 versus M Pro, so on and so forth. What is really different between these systems is that the number of transistors is there, okay? But then the question is how big this die can be, right? Can I have a gigantic die? Can I have a die as big as this kind of size of this table, right? And the problem with this having this big die is that the technology, as you kind of increase the die, is that you're more vulnerable to faults and errors, okay, to failures. Because essentially the way that we build this is what we call the reticle, this mask that we put. And this mask cannot be like really bigger than some size because of the technology limit. Plus, if you think about like the chance of failure as the function of an area, as your area grows, the chance of failure also grows, okay? So if NVIDIA really, really wants to kind of increase the size of their matrix multiplier, because they clearly need it, right? They have billions and billions of parameters. So ideally, they want to have something that can boom in one go, in one clock cycle, multiply all the elements because they have billions of elements, let's say. But in order to do that, they need this massive, massive GPU. So what they do is that instead of like making the individual dies bigger, they go with this idea of what we call chiplet systems that essentially say that, okay, I don't need to make this gigantic die. What I can do is that I can break this die into smaller dies like this. So I can have 9 smaller dies. But the big thing is that I need to figure out a way that they put this into some form of a substrate that the connection between this guy and this guy is as fast as if this was a one unified dot, okay? So this is what we call the heterogeneous integration or 2.5D integration or 3D integration. So it's actually the integration technology is kind of saved the date for us and allowed us to build this gigantic things. So as you can see, like, you know, they also showing you this, that this is die number 1, this is die number 2, but they managed to have one unified system, okay? How do they do that? They actually managed to build this very, very fast integration technology that apparently they give you like 10 terabytes per second or these massive numbers. And this is mainly because the way that we figure out how to actually build those systems, how to integrate them really, really fast. I'll actually have a few slides to talk about kind of different options for this, but generally this is kind of like the basic idea of how we can actually do that. And then as you can see, they also not only just make these chips like nicely close to each other, as you can see, the memory is also kind of in the same boat with the rest of the system. So you see that there is like this HBM3E generation that is also on the same sort of a substrate with this 2 dies, which means that GPUs can very quickly read data off of this memory. And they have this massive 192 gigabytes of memory, but they can also get significant amount of bandwidth out of the system. So you can actually read and write very fast. As a result, they're getting this, significant numbers in terms of flops. Flops means floating point operations. So think about like higher the flops means that I can do more floating point operation. Think about every element-wise matrix multiplication is one floating point operation. So if I can do 10 petaflops, it means that I can do 10 to the power of, is peta 12 or 15? Honestly lost count, but I can do that many number of floating point operation per second, right? So, and then of course, if this goes higher, it means that now I can do these things much faster. Now I can actually go toward this direction, right? So I can do GPT-5 and GPT-6 and GPT-7 and so on and so forth. And then the kind of like the machine learning community, algorithm community can also think about, okay, what would that buy us, right? Can I actually, by making more layers to my network, do much better things? And it seems that they can actually, and that's a very, very exciting news. Now that I can kind of provide this opportunity as a hardware designer, now we are kind of changing the world, right? So we are making AI really, really capable. So that's kind of like, the very, very exciting thing about this era of computer science, computer architecture, because now there is actually demand for really, really high performance systems. And then combination of these innovations at the hardware level and innovation at the machine learning algorithm level could lead into potentially very, very exciting things, as it's really happening at the moment. That's why NVIDIA is like this billion-dollar company, because people are seeing the potential. But it's not just NVIDIA. There's other companies that are also doing it very well in this domain. Okay. This is another example, and this is from the Apple LM1. As you can see, it's, again, here you see that they are part of the same fabric. And again, the reason that, for example, you get much better performance from your Apple machine compared to like a regular motherboard that you discretely put like a really good GPU and a really good CPU. The reason that Apple cannot outperform it is that things are very, very tightly integrated under the substrate, and the substrate can very quickly, move this data around. Okay, so you see that the CPU and the cache and the neural engine and the DRAM, everything is part of this quote unquote fabric, the substrate, and as a result, they can communicate to each other very, very quickly, and that's kind of like what's really the game changer in the system. This is the picture of M3 Pro, which I think is M3 is the latest and greatest, or do we don't have M4 yet? Okay. Yeah. So M3, as you can see, has this quote unquote unified memory, which again is the term that you put these things next to each other, but really the substrates kind of make this thing very, very fast. And then as you can see, they have tons of different things. So they have 18 core GPUs, right? They have 12 core CPUs. And by the way, pay attention to kind of like two class of CPUs that you see here. There is performance class and there is efficiency core class, right? And then as you can see, there's kind of everything is just one giant substrate, that things are still smaller dies, but they managed to put them next to each other. This is also, that's what I found in the internet, that this is apparently seems to be the microarchitecture of A17 and A17 Pro. I think these are the latest generation of Apple. As you can see, this is the performance one, and this is the efficiency one. So the performance one is the one that is kind of course, faster, but faster means more power hungry. As you can see, the big difference between the two is that this one seems to be 9 wide. So if you remember, we told you that, we pump out instructions, like, multiple instructions. In Boom Core, we talked about 4, but apparently this A9 Pro has 9 wide instructions, so they can actually read 9 at the same time. The choice of 9 is really interesting, because usually you go like 4, 8, 16, but I don't know why they chose 9, but it's interesting. Then you will see that they have like this physical register file, apparently 432 entries. They have all this, fancy branch prediction and fetch. I'm assuming there's some form of a tag and G-share and all those things going on there. As you can see, they have floating point register files and they also have integer register file. And this is usually the standard in most of these modern systems. But they have the same classic fetch, decode, and rename that we discussed in the class. Then they go to the back end of their system. And as you can see, they're kind of doing very similar to the way that Boom Core is also doing. They have per, instruction schedulers per unit. So they have separate these kind of schedulers. So they have this dispatch buffer for these kind of group of activities. They have another separate dispatch buffer for this group of activities. They have dispatch buffer for like load store queues. They also have the separate dispatch buffer for the floating point operations, right? And their dispatch buffers are 12 entries. But then they have this schedulers that is kind of like more complex. And the reason that the scheduler is more complex that there might be lots of kind of dependencies that things needs to be there. As you can see, then they have multiple of these functional units, right? And then they have their ROB, which is 321, which is kind of needs to be the size of like all these instructions that we have in the combined set of these instructions. And yeah, the rest is you can see there's ALU operation, branches, flags, addresses. There's load store queues. We have LD queues. We have SD queues, which is connected directly to a data cache. And then, as I said, we usually separate the integer operations from the floating point operations. Yeah, that's pretty much it here. And then if you compare the P1 with the E1, the real difference is things are much smaller. So the amount of kind of super scaling factor is much less. Instead of doing 9, we do 5. All the sizes are much smaller. The number of entries are significantly smaller, right? And probably some of these fancier optimization and some of those things that we discussed in the class, including load speculation or various form of speculation is probably less here to make things more efficient. Generally, the idea of having like a performance core and an energy efficient core in the same system is this is the concept that originally proposed by ARM called big little. So you want to have a big core that can do things very fast, but it's very power inefficient. And you want to have a little core that can do very efficiently, but it's not as fast. So what you will do is that you turn off your big core most of the time. You have your little core for like, sending and receiving small kind of, messages and all. When you have an actual thing that needs to be done, then you offload it to the big core. Okay. So in your cell phone, for example, when you turn it on, then you will see things and say, okay, now this is like probably the first thing that happens is your little code gets involved. But then when you start opening your phone and start, I don't know, doing video conferencing or browsing, then that's when your big code will kick in. And then you have a bunch of little cores and a bunch of big cores together. They actually do hand in. Okay. Any questions? I'm not sure, by the way, that this is the kind of correct design. I'm just finding it in the internet, but seems legit. So if someone can confirm, that would be great. But seems.
And I sent you an email just now, the document that this came from.
Oh, okay. I see. Okay. Cool. Yeah. So this is kind of like just a quick overview of what is going on now. Let me actually give you a little bit more on the chiplet technology and the need for the chiplet technology and kind of like a little bit more detail on that. The chiplet itself is kind of more of like low level. So just wanted to give you a quick overview, but if you're interested, go and read it. This is from this famous paper from AMD. AMD actually is one of the pioneers of chipletization. They kind of started and picked it up way before the other companies, but now almost every major company has chiplet-based systems. So what I'm showing here in this figure number one is essentially this is kind of like, as I said, this is the Moore's law. This is kind of like, yeah, double every kind of 2 years. In reality, it's kind of like, as the figure shows, it's double every 2.5 year. And the difference between this one and this one is that this is at the transistor level. This is more at the actual system level, at the server level. So really what we are seeing now is that near to 2020, we are getting to what we call the exaflop, which means that we can do massive amount of computations, right? But this is not just one chip, it's the combination of multiple chips together that can give you that. Because we always, similar to the system that we have hierarchy in internally, you can build a really nice chip, but then you can have multiple of these chips into your server, and then you can have rack of these servers in order to build a very big data center, right? So the data center, of course, you're not going to get the quickness of a communication as you would get in the chip level base, but still there will be some form of like really fast communication between them. So that's where you're going to get this kind of exascale, computation. Okay. The second trend that you can see is kind of like the trend of the size of the transistors. So in 2004, we kind of were at 90 nanometer. This is the length of each transistor. In 2020, we are around 7 nanometer. These days, we are actually managed to get to the 4 nanometer too, right? So like, these recent Apple products and so on, there are 4 nanometers. There's also like they're trying to get lower. But as you can see, this process slowed down a bit because building like really, really high-end fabrication is really costly, very, very difficult. And in fact, what used to be this higher technologies, there were many, many manufacturing fabs. For 7 and 4, there's literally just one company, TSMC, that can build this. Because everybody else is not, they just don't have the technology and the expertise to do that. And that's why US is actually paying TSMC to bring their technology back to the US. So they're actually building a significant manufacturing facility in Arizona to re-enable US to be able to build chips at a very, very high-end technology node, because Intel and all, unfortunately, they couldn't kind of like, they have this, but they don't have this. So this is kind of like also another very interesting kind of trend, more at the hardware level. But an interesting thing is like, the cost, or in other words, the yield per so the cost per chip is significantly higher when we go to a lower technologies, right? So that's the kind of like the motivation of not making your chips much bigger, because in order to have a functioning chip in these lower technologies, you are paying much, much more higher cost, about 6x more compared to what we had in like 40 nanometer and so on. Okay, so this is kind of like the motivation of building chips like this. That what used to be like the top figure, which you had a wafer and you cut it down into dies, big dies. Now what you can do is that you can make it much, much smaller. This is what we call chiplet. Then you still have defect here, but the number of defects that you have here is much less than here. Then you can then assemble them like this, and then you will hopefully have the similar performance of that one big one, if you can actually manage to kind of like connect these fast enough. Okay, that's kind of like what we are doing now, and that's kind of what keeps this industry going. That we can actually now build. And the nice thing is that now I can actually go beyond this, because if I can do these little things together, now I can actually build something twice as large as this, right? And that is what is happening with like these big GPU cores. There's also some other companies that they're doing wafer scale computing, right? So there are companies that has this gigantic wafers, and they're doing the entire computation on that. And And that's just thanks to this, that I can still have little chips, but I can combine them together. Okay. So this is the example of this Zen course, right? So this is actually, this is commercialized, and almost all the Intel and AMD and Apple processors these days are based on this. So this used to be the monolithic 34 core chip. They had this 4 Zen cores, and then combine them together. Now what they have is that they have these much smaller 2 4 Zen cores, but then they have these, then they make it into 4 chiplets, and then they still have the same thing. What is different now is that you can see that they actually have these other cores. They have this, what they call infinity kind of like connection. This is like how they actually can connect to these other systems. They also have this IO based kind of peripherals to talk to the IO. They have this DDR to talk to the memory, and so on and so forth. So they're actually kind of like adding this additional components in their system in order to be able to talk to the rest of the system and to each other, to make this connection very fast. Pay attention to the numbers. Like, for example, this was 777 millimeters squared. But this is basically 213 millimeters square per chiplet, which the total area is pretty much the same, slightly more, but then you'll essentially have much, much lower cost per chiplet. Yeah.
How difficult is it to design a good interface, a fast interface, and does it introduce any overhead?
Define interface?
Like between the chiplets, the connection.
So the connections, there are tons of different options. So in the past, we had this kind of system in package, right? So this is what we had in early 90s, okay? Then we started to have this. So this is kind of like where things start getting very interesting. This is what we call 2.5D, right? So essentially you have these 2D chips, but then you kind of like integrate it on this substrate, which is different than this substrate. This is usually what we call a silicon interposer. So it's like a layer on top of what you had in the past in the package. Okay. Then there was this additional technique. So this is what Intel provided, and this is called silicon bridge. Actually, I think here is much nicer to show you that. So this was what we had originally, okay? So we had the package substrate, think about the PCB, and then you had this different dies, and then this different dies had this what we call bumps, C4 bumps, and then they connected to each other. One thing to remember is that when you're actually trying to go off the chip, the connection is really slow. The reason for that is that the capacitance of these bumps are really large, okay? That's why it's really slow to go from one chip to another chip, go outside that and go inside back, okay? And then also it's because of the distance. Literally, the distance that it takes for this to go is higher, so the latency is high, okay? Then people start thinking about, okay, how do we make this faster? And one of the key solutions is this silicon bridge, okay? So what they said is that, okay, I don't need to change the substrate completely, but I can have this quote unquote bridges that kind of connects these two to each other using the silicon. Then the difference between this and this would have been that I can then use a different technology to connect the chip to the bridge and from the bridge to the other. Okay, so this is one reason that make this much faster. You call EMIB or enhanced something bridge. I forgot the name, but this is the Intel technology that they introduced and they're still using it. And then people start thinking about, okay, let's actually get rid of this package and let's kind of expand this into a layer of its own. This is what we call an interposer. So essentially now we have kind of a tree layer. So we have the package, we have the interposer, and then we have the die on top of the interposer. So now everything is kind of connected to this interposer. And the nice thing is that, again, since the connection from the die to the interposer is very different than regular package, now things are much, much faster. The problem with the interposer is interposer cannot be really, really large, okay? So you have to either have multiple smaller, like if I have a massive design, I cannot have like a massive interposer because interposer is a very fragile, it needs mechanical supports and so on and so forth. And the last thing that people have found was essentially this kind of like silicon bridges that it's similar to the interposer in the notion, but it's kind of like, moving, using a different technology that like, this layer is kind of like a regular interposer, and then you have this silicon interposer inside it. So this is kind of more scalable compared to this one. Going back to this figure, essentially, as I said, this is just what we have, an NCM or system in package. Then we have this interposer technology. Then we have this bridge technology. Then we kind of like improve this interposer technology with having high density interposer technology. But then what's really make things even more interesting is that now we can build things 3D. So not only we can do things like this, but now we can also build die on top of each die. So I can build another die here, and I can connect these two with what we call TSV, or true silicon vias. Okay, so now I can actually have what used to be 2.5D is now true 3D. That now I can build on top of each other as well. And this is what we're going to have as kind of 3D system on wafer. So now I have this, and also I have this. So some of them are kind of like this, some of them are like this, okay? And now the kind of the vision for future is that some of these can be also optics based, because these things are still electrical. If I can somehow make this optical, then we're talking about orders of magnitude faster communication between these two chips. Okay, so it's very, very interesting, also kind of like line of research that makes things optical. And then yeah, this is the 3D version. So again, AMD has this 3D cache idea that they actually put the DRAM on top of the chip. So now the chip has very, very fast access to their DRAM because it's actually built on top of it. So they can actually go really quickly. So usually this L3 caches can be put on top of the chip, which makes it very fast. So this is kind of like what we have these days, that we have the PCB underneath, then we have some form of interposer or layer of logic that have some bridge. Then we have, for example, let's say our GPU and our CPU, and then we have the 3D chips on top of that. So this is where we're going in terms of the technology. Did I answer the question?
Yeah, I have another.
Mm-hmm.
So from what I understand, for example, TSMC like 4 nanometer is not actually 4 nanometer. It's because like we do this 3D stacking. If you were to look at the density, it would be equivalent to a 4 nanometer process, for example.
No. So when we say 4 nanometers, we're talking about individual transistors, okay? But an interesting thing about these things is that what we call them heterogeneous integration, okay? So as you can see, for example, I have one die here and one die here. They don't necessarily need to be in the same technology, okay? They're heterogeneous in the sense that one can be at 4 nanometer, the other one could be at 45 nanometer, okay? When we say 4 nanometer, we mean that there is some 4 nanometer transistors here, but not all the chips necessarily need to be at that 4 nanometer. But for example, if this is 4 nanometer, then so this is memory. So it's still, this is the transistors in your CPU is 4 nanometer, which means that they're fast enough. But remember, transistors alone and CPU alone doesn't help you anymore. You need to bring lots of data from your memory and back to the memory. That's why we kind of come up with this connection technologies, right? So that's really what's happening.
So they actually are, like if you were to measure them, it would actually be 4 nanometer, the length.
Mhm.
Oh.
Yeah, and then if you're interested to actually look at their, so this is nowadays in order to achieve that, it's kind of the gate is kind of like this. So this is your channel, and the gate is kind of all around gates. And then usually the kind of, I think the radius is 4 nanometer. Any other questions?
Professor, is there energy consumption concerns when like the chip gets smaller and smaller?
Of course, so as the chip gets smaller and smaller, there are lots of power constraints. And then actually one of the biggest constraint is this. Because when it used to be 2D, then you had heat sink and kind of power, heat dissipators on top and bottom. But now this guy, the only way of, turning heat out is from here and from here. But all these layer between, the heat is kind of trapped. So the main actually issue of preventing us of adding this large number of layers or making them really, really big is actually the heat and the power consumption. And there are tons of research on how to do this power and this heat temperature dissipation, this power dissipation under the control. The second problem is as we move toward this, okay, now the second question is how do I even power up these devices, okay? And the interesting thing is that what used to be kind of like, yeah, I'm just going to add this here. Now I need to kind of somehow route the power to here, right? And then I can only, for example, route the power from the corners if things are in the middle, right? Because I can now, for example, add lots of things here because of the limitations. So now I need to kind of like route power from the corners. And now things that are in the middle of the chip is kind of we're seeing a large amount of drop in the voltage because voltage is usually the function of distance, right? So we call this IR drop, right? So the resistance gets higher, so the voltage goes low. So again, there are lots of interesting research at the circuit level, the design level to think about these problems.
But if you use optics, you should keep up.
If you use optics, things gets much better because much more efficient, right? So that's one of the key reasons that people are interested in optics, because first of all, the form factor much smaller. So we are talking about really, really, really tiny pins, but also things are much faster. The problem with optics is that this constant conversion between electrical and optics, right? So you need to transfer from optics to electrical. You electrical to optics, then send it optically, and then change it back to electrical. And that is the main challenge these days. All right. So, and this is kind of like, that last picture I want to show you. This is AMD 64 EPIC. That has the GPUs and CPUs and all those great things together. So as you can see, it's just kind of like this massive machine that has, the GPUs next to each other and the CPUs next to each other. And they have this CPU GPU fabric, and they can go like, this is what they call exascale computing. They can go such a huge number of chips together based on this technology that they have. They can actually kind of mix and match all of these together. They can build massive GPUs and CPUs together based on this chiplet technology that they have. So if you're interested, actually read this specification of the EPIC, which is kind of like, now it's kind of like the standard grade data, like server scale, rack scale kind of computation systems. They have the accelerators, they have the GPUs and all those things. Usually this is installed not at the PC level, but it's actually at the server level to get the computation that you want to have. Okay. Any other questions? All right, let's have a quick break. Then the second part, I want to talk a little bit about security too. All right. So the second part, I want to talk about kind of our research with triplets. This is actually what we do actively in our group. And then those of you who are interested, feel free to reach out. So the fundamental question that we are asking is that given that we are kind of moving toward this triplet regime, is there any interesting security challenges that one should think about? And essentially there are kind of three questions. There is actually three questions. I'm showing you two here, but there's actually a third one as well. The first one is, given that I'm using tripletization in order to improve performance, for example, or improve the cost efficiency, now the question is, can I use it to also improve hardware security? And I'm going to describe what I mean by hardware security and how can I do that. The second question is that since I'm moving toward tripletization and the fact that what used to be like a large monolithic design is now kind of this smaller design, the question is, can I actually think about computer architecture methods, microarchitecture changes that make the security more efficient or slightly cheaper or more capable, any of those things. And the third question that I'm not going to talk about today is tripletization introduce new challenges? Okay, so it's not about enhancing security, but it's actually reducing security. Because for example, if you remember, we talked about Rollhammer, we talked about side channel attacks. Since that we are moving toward tripletization, the question is, are these problems going to get worse or are they going to get better? If they're getting better, why? If they're getting worse, why? Right? So these are lots of new research questions that one needs to think about and try to address. I'm going to talk about these two, but I'm going to leave you with the third question. If you're interested, we can talk later. So there are like tons of things that makes this questions interesting. As I said, rise of chiplet systems as we described it in the few slides before, but also kind of like the rise of the attacks as we discussed time and time again in this class, that these are kind of two trends that we are seeing in the computer architecture world, that people are interested in chiplet, but also generally hardware side channel attacks and Rollhammer attacks and so on and so forth, they're also increasing. So these two together seems to be a very, very hot area, very, very interesting area that can be actually combined. And then the third is, as I said, there is a general interest in US governments in securing the hardware systems. And this is mainly fueled by the fact that they realize that they're too much rely on external companies and entities and countries for chip manufacturing. And they saw the fragility of this, especially during the COVID and the events that after that, once they stopped being productive, things got really, really scary, right? Like, there was shortage of chips in various different places. And that could create lots of actual, challenges, defense and security challenges for a country like US, okay? So there is this significant amount of investment called the CHIPS Act. Billions of dollars are going to be funneled into semiconductor companies in order to be able to build chips back in the US. Okay, so most of it goes to Intel. And as I said, big companies, big manufacturing facilities are being built in Arizona and Ohio because of that. So the first question, as I said, we want to improve hardware security. So let's actually see what is the challenge that we are trying to fix. And we kind of discussed this a little bit in the past, but essentially the idea of chips is that so far we always assume that the hardware is secure, right? And that we design the system, and usually this is the final stage of your design is this file format called GDS2. You send this GDS2 to a foundry, and the foundry will gonna actually mail you back the actual chips, the physical designs, okay? But the question is, yes, I can make sure that this design is secure because it's done by me. I can use all the techniques that I know of in order to make sure that this design is secure. But when I'm sending it to this kind of external foundry, I have no control over what is actually being built, okay? So if the foundry or someone within the foundry do something malicious and sending these chips, and these are chips that are not the same that I think it is, then I'm in trouble, okay? This is actually a very well-known problem called hardware Trojans. That the equivalent of that is software Trojans we kind of discussed in the class. The idea is that I can, for example, I'm giving you a toy example of, like, let's say I have 3 inputs and an S as an output and a P as an output. But then the adversary, what they do is that they're adding this additional gates to my system. Okay. And this additional gate with some inputs that is also added by the adversary, what it can do is that it can actually change the output of the system. Let's say, for example, that this gate was supposed to be 101, was 100 as the input, and the output should have been 1 and 0. Okay. If you actually know a little bit about logic design, you will see that if I turn this input from 0 to 1, then what will happen is that this bit will flip to 1. Okay. So by changing this input, I'm essentially impacting this output, although the inputs are still the same. Okay. So now think about that. For example, this bit is an important bit. So for example, let's say that this is the privilege bit that we talked about in the class. That remember, for example, for the T, we had like user level and privilege level, and we showed that, you know, the difference between really the T application and non-T application was this. Let's say actually the circuitry that kind of computes that privilege bit is this. And the adversary, what they do is that they're adding this, and they have the trigger bits. And whenever they want, at their will, they can change the privilege of a single application. So that would be a huge problem in our systems. And there's nothing that we can do at the software level. This is completely at the hardware level, and unfortunately completely hidden to the designer, because the designer thought that this was the design that they had. But when they're actually being built, the adversary managed to put this into their system. Okay. So this is the problem of hardware Trojan. And this is actually getting worse because, as I said, we are relying more and more onto our external foundries. That's one of the key reasons that we want to bring them back in the US, because now we can kind of make sure that they're actually doing what they're supposed to do. So what do you think would be the solution to this? Anybody has any suggestions of how do we fix this problem?
What has a house foundry?
Yeah, just change the don't send it out. That's good. That's basically what we're trying to do. Yes. But can I do something else, at least if I want to still send it out? Yeah.
Have encryption between the servers. So like, for example, you have a rack at TSMC that is dedicated to you. TSMC does not know the key, right? Does not have access to it.
Sure.
You have to be another authentication factor such that if this bit is I, but this other bit's not, you've been compromised of some sort.
Yeah, maybe. Good observation. Yeah. So there are kind of two solutions. One is kind of similar to what you're saying. It's kind of called logic locking. So there is kind of like some form of authentication going on that only particular sequence of bits should result into something that is meaningful. Another one is essentially making it hard for the adversary to know where to put things. So essentially make it random guessing. This is what we call obfuscation. Okay. So the idea is that if I have, let's say, a circuit like this, okay, if I kind of like remove some of the connections, okay, so those that are grayed out, I remove them, I obfuscate them. I'm going to explain how we can do that. But for now, let's imagine that magically I can do this. Then now if you think about this and this, then the adversary cannot differentiate between this and this, okay? Because both of them are connected to this one. I can know which one is this, but I don't know which one is 4 and which one is 2. Because forget about the kind of the location, so I can move this around. It's just based on the connection to 5. Both 4 and 2 are connected to 5. Everything else is obfuscated. The only thing I see is that I see 2 gates that are connected to Y, but I don't know which one is which. Okay? So in other words, what is happening is that I'm forcing the adversary to this. So let's say the adversary really needs to know which one is 2 because they want to kind of add their gate here. I'm basically reducing the probability of a successful guess to a random guess. So in this case, 50% chance. And then you can imagine that if this number goes up, then the adversary success rate significantly diminish. Okay, this is what we call obfuscation. So now the question is that how do we obfuscate? Anybody wants to suggest how do we hide these connections from the adversary? For those of you maybe a little bit, do you guys know how do we actually build chips? Like, have you taken any course of like, metal layers, multiple metal layers? Okay. For those of you who know, this is usually how we build chips, okay? Chips are kind of built in layers, okay? So we usually have the silicon substrate, okay? And then in silicon substrate, then we need to first build our transistors, okay? Transistors are usually like either you etch things to kind of create trenches, or you let things grow out of your silicon. So you kind of add these kind of chemicals and you let it grow, okay? So you either go down or go up, okay? Then you will get your transistors, okay? But transistors alone, of course, is not anything useful. You need to now connect these transistors to each other. So how do you connect these transistors? You connect these transistors using what we call metal layers. But the metal layers, you think about it as like a very multi-layered things, okay? Because you cannot connect things in one layer because, for example, this one needs to be connected to this one, but then this one also needs to be connected to this one. So there needs to be some notion of height, okay? So we have these layers. We usually have up to 7 or even sometimes 9 layers of metal, okay? So we have metal layer 1, metal layer 2, metal layer 3, and so on and so forth, okay? And then there are algorithms that decide that which of these layers you should use and so on and so forth. So this is how we build our computers. And usually then the output of that is at the top layer. So if this system needs to be connected to somewhere else, there are connections on the top to make this connected to the other layer, okay? So the idea of how do we obfuscate layer is essentially that's what we call lift. So essentially, if I connect, the connection of these layers are happening on the top layer, and I divide this into 2 pieces. So I build this piece first, and then build this piece next. When I'm building this piece, all the connection in this higher layer is unknown, is obfuscated, is removed from the lower layer. Okay. So in other words, if I go back here, I have this end-to-end connection. These grayed out are top metal layers, okay? So when I'm building the lower metal layers, I'm going to build this gates because all the transistors are happening in the lower layer. Some of these connections are also happening in the lower level, but everything else is, all these grayed out ones are the top layer, okay? So this is what we call split manufacturing. We split the manufacturing phase into 2 parts. The first part is lower parts. This is untrusted part. This is the part that we send to a manufacturing facility number 1. They build this, and when they're building this, they have no idea about the connections at the higher level, okay? Now we're going to get this back. Either us or some other foundry is going to do the top layers, okay? So this way, we're going to ensure that the system is secure because the untrusted facility never going to see the top layer of my design, okay? Usually this lower level, we call it front end of line or FUL, okay? Which contains the gates and some of the wires. And this top layer is, we're going to call it the bottom end of line. And we top, BUL, which is kind of usually just the wires, okay? And as I said, the key assumption here is that this top layer is manufactured differently at a different place than the bottom layer. As long as the bottom and top layers manufacturers don't talk to each other, don't collude with each other, then we are good to go, okay? So now the question is, how do we kind of decide, which one to lift? What's the best strategy to lift? And this is usually based on graph theory. Think about this as a graph. Think about this as your nodes. Think about these as edges. We want to make a graph similarity problem, essentially. We want to make this thing similar to a graph, an obfuscated graph. Okay, there's this very well established metric called K-security. The idea of K-security is this: that if I have a gate like this, if I have a circuit like this, I make it like a graph like this. I color it based on the different types of gates, and I have edges that kind of shows the connection from one gate to another. Now, the issue of K-security, the definition of K-security is that if I remove some of these edges, how easy for the adversary is to differentiate between the gates, okay? So for example, let's say I have this design, these are my inputs, and these two are my outputs, okay? So I have 5 different gates, 1 and 3 are similar, 2 and 4 are similar, 5 is different, okay? So let's say I obfuscate this based on some algorithm and I got this, okay? This is what I get. So now the question is how good this obfuscation is. Now the question is how easy it is for the adversary to know which gate is which, okay? This is where we define K-security. For example, let's look at U and X, okay? We call U and X too secure because essentially by looking at this, okay, and knowing the original design this, the adversary can say either one of these two is 1, the other one is 3. So essentially for gate U, there are 2 options, either 1 or 3. For X is also 2 options, either 1 or 3. So we call this too secure because there are 2 possible gates, 2 possible candidates for this gate, 2 possible candidates for this gate, okay? And then if you're wondering how we come up with this, essentially you have to see that, you know, if you see this, what are the possibility of 1 to 5 this cannot be 1, this cannot be 4, this cannot be 5, so it can be only 1 or 3, okay? So it can actually work out the math to see how it works. Same issue if you look at 2 and 4, you will see that V can either be either 2 or 4, similar for W, so we say that gates 2 and 4 are too secure as well, okay? Then you look at gate number 5 and you will see that number 5 is actually, there's only one option. So by looking at Y, I can immediately say that this is gate number 5. So in other words, gate number 5 is 1 secure. There's only one option for gate number 5, okay? So the notion of K-security is that iterating through your gates and measuring the amount of their security. And then you need to decide where you want to stop. So for example, if you want the minimum amount of security, then you probably want to have all your gates have X amount of security. So for example, say my design demands that everything is 4 secure, okay, or 5 secure. If it's that, then you need to lift a lot of wire, right? If your design says that, you know what, some of the gates is okay if they're a little bit less secure, then you can do it more adaptive. But the whole thing is that now you have a metric to be able to measure this, and the rest is really just design dependent and manufacturing dependent, okay? So there are multiple problems with K-security. The first thing is the performance cost, and the second thing is the security guarantees. The problem with the performance is that as I move the connection to higher gates, the latency between the connection goes higher. So you genuinely more interested to have connection in lower level metal because it's less distance to travel. But this K-security is the exact opposite, right? It tells you to go higher and higher, which means that you're kind of trading off your latency with security. The second is that it's not guaranteed that you can always achieve K-security as you wish, because sometimes it's just you are forced to do this, okay? But then the interesting question is that when we are moving to tripletization, can I do a little bit more? And this is actually what we did recently in our research. That, you know, we used to have this, but I told you that we are already moving toward this. That what used to be a single design is now multiple triplets. So why don't we actually use this in order to further obfuscate our design? Okay, so this is what we're going to do, is that what used to be lifted wires is now lifted wires into 2 different directions. Okay, and by the way, these two are flipped. Okay, so the FUL here is FUL here. So usually the chiplets is flipped, so the device is in the higher level and the design is in lower level because the substrate, so you put the chiplets in the substrate and the connection is in the substrate. So it's a little bit different than regular systems, okay? So this used to be our thread model, which we said that, okay, we have a bottom layer and we have a top layer. These two shouldn't trust each other. The thread model for split manufacturing with chiplets is kind of like this. And we have our design, we chipletize it, we send it to multiple different manufacturing facilities. And then at the end of the day, all we need to do is that we need to kind of combine them all together into this common substrate. As long as these don't talk to each other, and this facility that kind of connect them all together is trusted, then we are good to go. We actually have a trusted system. Okay. So now the question is, how do we actually measure security for a chiplet system? So what used to be something like this is now something like this. There are kind of like, different interests. I'm not going to go through the details of this, but you can think about that kind of case security works, but also doesn't work. The reason that it doesn't work is you need to compare chiplets with and without, right? So you essentially need to compare this with this entire system, this with this entire system, and this with this entire system. But the problem with chiplet is these are not the same size as the original graph that you had. So you're essentially comparing a smaller graph with a bigger graph, which is not something you want to do. The second problem that you have when it goes to the chiplet is connections between chiplets versus connection inside chiplets are very different. So the edges are actually different. You don't have just one edge. You have two types of edges. You have inter-chiplet edges, you have intra-chiplet edges. So you have to be careful about the difference between these two. Okay, so in order to do that, you can actually come up with solutions. If you're interested to the solutions that we did, what we tried to do is that we had these two design guidelines. We wanted to make each chiplet very similar to the other chiplets in the system, so that if the adversary see one chiplet, cannot tell which one is which. Then the second thing that we want to have is that combination of all the chiplets should be very similar to the design that we had originally. So these are the two things that one needs to do. Then we come up with this kind of metric of split score, which essentially what it does is trying to measure the similarity between chiplets and between their nodes. And one thing you will see here is that there's difference between types of edges. Some of them are more important than the other. I'm not going to go through the math. If you're interested, just check it out. This is the formula. This is how we calculated it. If you have a question, let me know. But eventually what will happen is that you get some score similar to the way that we got the case security. Okay. Now the question is that, remember, we had two guidelines, right? We want to make these chiplets similar to each other. Okay. We call this intersimilarity. Between the chiplets, we should be very similar, which means that if I compute the similarity score of these two, I want this to be close to 0, very similar. And then the second thing I want to do is that I want to also have what we call intrasimilarity, which all these chiplets together should be similar to the original chiplet. Okay. Then you might ask, okay, how do we combine intersimilarity with intrasimilarity? And this is the similar way that we do it for multi-layer optimization. You use some factor to kind of regularize this, and then you can choose which one of these two is more important to you. If you only care about intersimilarity or only care about intersimilarity, you can decide which one to use. And then we actually evaluate this. Let me show you some results. So for example, if you look at this design that we looked at, so this is actually showing you the metal cut layers, and this is showing you the number of chiplets, and the color shows you the delay overhead. And this z-axis shows you the level of trust. As you can see, you see this kind of behavior that as you increase the metal cut layers, as you increase the number of chiplets, of course, you're kind of going up in terms of the security. And the designer can basically choose a point in this 3D graph. So for example, let's say for practical reasons, you don't want to go beyond metal layer 5. And for practical reasons, you don't want to have more than, let's say, 4 triplets. And that will give you, for example, an operating point like this. But maybe you can let one of these to be flexible. Let's say I can kind of change the number of triplets. That will give you kind of like an operating range within this range or within this range, right? So this is kind of things that you can do as a designer to make this system more interesting. Another important thing when you're considering these type of designs is the complexity of the design, the number of gates that you will have. So as you increase the number of gates, various different things changes. Your overheads usually go up. For some of them, it doesn't go up. For example, the violent overhead is significantly going to increase because you have many more designs and you want to kind of tripletize these designs. So there are things that one needs to also consider when we are using this kind of designs. There are also tons of other things that one needs to think about. For example, if I have performance in mind versus security in mind, which one should I optimize for? Should I optimize for security? Should I optimize for performance? Or are there ways that I can combine these two together? So these are actually active research that these days we are looking at. Yeah.
Is this type of like obfuscation common in like consumer electronics, or is it mainly just for like military type stuff, type product? Or
yeah, this is well, I mean, all the companies who cares about their security would use this kind of systems, right? So this is, I mean, security used to be more of a concern for like more sensitive companies, but these days every company is worried about these things. Yeah.
So I mean, I don't know if you can say for sure, but like even consumer electronics.
But yes.
Wow.
But also think about this, that like consumer electronics, their eventual users or customers might be like these sensitive companies. So like think about banking, right? So Intel, if they have I don't know, Bank of America as their customers, they want to make sure that their system doesn't have shortages, right? So this is also kind of like that. But yeah, you can do this tiered version. Like if it goes to a laptop, maybe whatever. But it's if I'm selling it to Bank of America, maybe I need to make sure that it's not Trojan. Right? And of course, this design has its own limitations, such as you cannot really tripletize everything. You are increasing the cost, you're increasing the overhead, you're increasing the power, and so on and so forth. These days, we are also looking at this more at the IP level and more complex level. So for example, if I have design like this, that I cannot like break things down easily. Some of things I can break down, some of them I cannot break down. How can I, from this on the left, I can go to this on the right? How can I kind of like move these things around and tripletize them in a manner of which that I get both security and performance at the same time? So these are kind of line of works that we are very interested in these days and looking at it. All right. The second question is, if you remember, I asked that not only we want to improve hardware security, but we also want to think about tripletization as an opportunity to rethink some of these computer architecture problems that we have. So if you remember in the class, we mainly talk about kind of like this on the left, right? So we said that there are these dedicated units. For example, you have a trusted execution environment that you put as part of your SoC to kind of do these interesting things for your system, okay? And then this could be either within your core, like very deeply integrated, or you can have it as kind of like some other components within your SoC. But now that we are moving to this kind of chiplet-based systems that I told you about, then we have new opportunities. We can have a dedicated chiplet for the security, or this connection that I told you about between chiplets. Maybe I can push some security checking and security operations within those connections, right? So there are tons of new opportunities in terms of where do I put those kind of security services that in the past used to be just like this, okay? So we are actually doing lots of research on like where do we put this And what does it buy us? It actually gives us maybe more latency, better latency, maybe give us more bandwidth. Maybe we can share a little bit more, so it gives us a little bit more area or power overhead, power efficiency, and so on and so forth. And so these are kind of like to give you a little bit of benefits of how this would be helpful. It simplified the design of the cores because now you're taking out the security and put it some form of a centralized approach. It helps you with doing hardware reuse. It helps you to customize for security because now everything is centralized. It helps you with reconfigurability and all those things. And it can help you with immunity against Trojans. In terms of the cost, it actually would be very cost efficient once you have a large design. So at some point, like while originally may not be cost efficient if you have just one chiplet, once you move to a large number of chiplets or different variants of chiplet, you will see that it's actually the cost is beneficial. And then you can think about the design as kind of like the variation of the design that we had. So in the past, we had this thing here, right? So we had our security closely integrated into the SoC. But what we're suggesting is that we can have something like this, that your security is kind of centralized. But interestingly, you can actually have both, right? So you can have a little bit of security close to your cores, and you can have a little bit of security as kind of a centralized approach. So together, you can have actually a system. And this is what we think that would be the future, that the future of our computer architecture would be some form of combination of a chiplet-based centralized versus what we had traditionally in our systems. We give you, there are some examples. If you're interested, take a look at them. Things like memory safety that we discussed in the class, cryptography, malware detection, so on and so forth. This would require, for example, some changes in the core design as well as the changes in the actual kind of like, you know, the chiplet design. But again, if you're interested in any of that, we can talk. Yeah.
So of all the diagrams that you've shown for the security, you've shown the chiplet for the security chiplet and like off the chip instead of like stacked 3D on top.
It could be also stacked 3D on top. There's actually, we had another figure here that there was also a third one, the fifth one that could be your chip and then the security on top of it.
Gotcha. So I kind of see that as more like a near-term solution. Does that make sense? Because like you could just put it on top of the existing design essentially with vias that are they're connected to, right?
Yeah, I think at the end of the day, it depends on sort of bandwidth that you need and latency that you need. If you really need to be very close to the design, then probably you have to either deeply integrate it into the design or, like as you suggested, put it as a 3D chip. But if you like, okay, I can kind of tolerate a little bit of latency going in and out, then I can probably go with like either of these two options here. And remember that chiplet gives you really fast communication anyway. So you're not really paying that much of a penalty of going outside. But you can definitely, there are some rare cases that you definitely need a lot of bandwidth, very, very low latency.
So in addition to that, you were talking about the graph theory behind the K security. Has there been research in active interposer implementation methods for that, or?
Not that I know of. There might be some form of active interposer for that, but I don't know. All right. I guess that's all I have. Yeah, that's all I have. Don't forget that your exam on Wednesday. If you haven't watched the review, also watch the review. And don't forget your final project. And as I said at the beginning of the class, don't forget the review. Does anybody have any final questions?
For the final, how much were you expecting to know for each of the different presentations?
How much do you need to know? I would
At
say,
what level of it?
yeah, it's kind of know that what was the solution about. So yeah, not the like the nitty gritty of like the exact solution. Yeah. Yep.
Is the covert channel championship like individual, or do you still work with a partner?
You can still work with a partner. Yeah, just what?
But if we do paper review, then it's individual.
It's individual, yes. Anything else? All right, guys, thank you. See you on Wednesday.